So, welcome back to lectures on engineering mathematics 2, and this is lecture number 40 on complex form of Fourier series. So, today in this lecture we will discuss the another form, a slightly different way of writing the Fourier series, and that is in the complex form. And we will also look into what will be the form of this Parseval's identity for the complex form of Fourier series. So, this was the series which we have already discussed. If f is an integrable or piecewise continuous function, then we can write its Fourier series, and these a n's and b n's are called the Fourier coefficients. So, these a n, the expression for a n we have discussed already, is 1 over pi and then f x cos n x, and for b n it was f x and sin n x dx for n 1, 2, 3 and so on. We have to use these Euler formula now to convert into this so called complex form of the Fourier series. So, this cos n x, this appear for example, here in the Fourier series, also in the Fourier coefficients. So, this cos n x can be replaced with the help of this exponential formula e power I n x and e power minus n x divided by 2, and similarly for sin n x also we have e power I n x, e power minus I n x, and then divided by 2 times I. So, now we can replace in the Fourier series. So, a by 2, and then this cos n x is replaced by this Euler formula, also this sin n x is replaced by e power I n x minus e power I n x divided by 2 I. So, we can now do some simplification, because the e power I n x is present in both the terms. So, we can take this common e power I n x, also the factor half will be common, and then we have a n from this term, and when we multiply and divide by I. So, this will become minus sign there, but there will be I times b n, because it was b n over 2 I, and when we multiply I both the places. So, that will be I b n and then 2 times I square, and that is minus 2 there. So, that minus 2 is considered here, and similarly for the second one. So, we have e power I n x, e power I n x is present at these two places. So, e power I n x we will take common again, and then half factor, and then similar setting can be done here, but this time there was a minus sign. So, it will come automatically as the plus sign. So, we have the form in the complex numbers. So, if we set here for this first complex number half a n minus I b n a new number, new name c n, and for the second this combination of the coefficients, if we call it k n as half a n plus I b n. So, having these two or new numbers k n and this c n, we can now rewrite this Fourier series as follows. So, the Fourier series of f will be for half a naught we have defined as c naught, which is also coming directly from this definition, where the b 0 will be set to 0 naturally, because b 0 is 0, we start b with b 1 and so on. So, here again the c 0 is half a 0, which is replaced here by this c 0. The second, this is c n, and then the third place here we have this k n. So, that is the complex form of this Fourier series, with having these coefficients, the c n half a n minus I b n, which is equal to. So, we will further simplify the final expression for c 1 c n, and also then again some more simplifications will take place for this form of Fourier series. So, we have the c n half a n minus b n, and we know the a n and we know b n. So, that was in terms of this f x cos n x, and the other one b n was this f x sin n x. So, by substituting these a n and b n here, we have a more simplified form f x cos n x minus I sin n x, and this cos n x minus I sin n x we have written in terms of again this exponential function e power I n x with this integral minus pi to pi f x e power I n x dx. So, we have the C n with half of a n minus I b n, and final expression in terms of f x we have 1 over 2 this f x e power minus I n x. Similarly, we can do for k n, and k n is half a n plus b n, where half the similar to this term we have 1 over 2 pi, and that f x, this sign will be replaced by the plus sign now, that is the only difference, and finally, we will have in the integrand here f x e power I n x for this k n x. What we should also realize now that for C n the expression has e power I n x, and for k n it is e power I n x. So, the only difference is with the sign. So, we can say that the k n is equal to C minus n. If we replace this n here by minus n, if we replace n by minus n, then we will get exactly k n there. So, we have this relation between k n and C n. So, having this, now again we are getting back to the Fourier series. So, the Fourier series is C naught, then C n, and then k n here. So, the k n can be replaced by the C minus n. Then we have f can be represented in this in a compact form, having this summation from minus infinity to plus infinity, because this C n is this k n is nothing but C minus n. So, in this form, when n is 1 we have C 1, but at the same time we have here C minus 1, then we have C 2, then is this place we have C minus 2. So, all this plus and minus are appearing together here, and the C 0 is already there in the front. So, in this compact form we have all C's with negative integers and also for positive integers. So, C minus n and C plus n, and e power this I n x will also take care automatically for the negative values. We have the for C also we will have the negative values, and automatically C power I when n is a negative number, this will be compensated. So, this form is exactly same as written in this compact form, which is n equal to minus infinity to plus infinity C n e power I n x. So, when n is 0 we have here C 0 e power 0, which is 1. So, we have just C 0 for n equal to 0, and that term will be also incorporated in this infinite sum. So, what is C n now? The C n is 1 over 2 pi f x e power minus I n x given here, and n is now 0 plus minus 1 plus minus 2 etcetera. So, this is the compact form of the Fourier series, much better than having those cos and sine. It is written in a very compact form C n e power I n x, and then the C n will be given by this integral. So, we do not have two coefficients now, only one coefficient is serving the purpose. So, we can write a general form, general in the sense when we have the interval from minus L to plus L, for instance. So, there will be slight difference. So, f x, so the function f can be written down in this Fourier series C n, and e power instead of I n x we have I n and pi x over L, as usual we have done before for this general form. And the C n will have now instead of pi we have L there, minus L to plus L f x, and again there will be slight change here. Instead of I n x we have I n pi x over L dx, and when L is pi this will reduce to this standard form. So, that is the case always we have. So, here n varies from 0 to infinity. So, this is the general form which we will use in one of the examples soon. Okay, so, if you want to find for example, this complex Fourier series of this function f x is equal to exponential x, and x lies between minus pi and pi, and then it is periodic. So, we can say f x plus 2 pi is equal to f x. Well, we know already that the complex form of Fourier series is given by this term here, and minus infinity to plus infinity c n e power I n x, and for c n we have the formula in terms of again exponential function. So, c n, if we want to compute now, 1 over 2 pi and then integral minus pi to pi, then f x we have e power x, e power minus n x, and then these exponential functions are merged here, 1 minus I n into x. So, there is an advantage here. For instance, in this case, if we are writing the complex series for this exponential function, evaluation of this c n is easy because we have exponential and we have again exponential. So, the exponents are added there. So, we have 1 minus n into x, and then we can easily integrate it. This is much easier than having those cos and sines and then computing a n's and b n's. So, now the integral of this is also easy. So, we have 1 minus n and divided by this 1 minus n, and then this x will vary. So, the lower limit pi and the upper limit we have pi, the lower limit is minus pi. So, here again we have 1 over 2 pi and then 1 over 1 minus n, and here we have substituted the pi for x. So, we have e power pi and e power minus I n x, and then for the minus pi here we have e power minus pi and e power I n x with the plus sign now, because x is substituted with minus pi. So, having this now e power I n x at these two places. So, e power I n x plus or minus, we will see in both the cases I n pi. This is cos n pi and plus. So, either here minus then plus minus. So, plus minus and I sin n pi. Sin n pi is 0 and this cos n pi is minus 1 power n. So, e power whether plus or minus I n pi is nothing but minus 1 power n. So, we have here minus 1 power n, minus 1 power n, and at this place also we have minus 1 power n, which we can take common now, and then we have e power pi minus e power minus pi. With this 2, this has written as sin hyperbolic pi. So, sin hyperbolic pi as per the definition is e power pi minus e power minus pi and divide by 2. For the cos we have the plus sign there. So, this exponential e power pi minus e power minus pi divided by 2 is replaced with sin hyperbolic. Minus 1 power n is for this e power I n x, and then the rest we have multiplied here 1 plus I n and also divided by 1 plus I n, and then so 1 over pi we have 1 over pi 1 plus I n, and then here 1 minus I n 1 plus I n. So, 1 minus I square n square, that is 1 plus n square, and minus 1 power n, and then we have sin hyperbolic pi. So, then we can substitute in the Fourier series this coefficient c n. So, then sin hyperbolic pi is a constant term, pi is also then outside, then we have minus 1 power n and then 1 plus I n divided by 1 plus n square, and then e power I n x as a result of this Fourier series. So, what we have observed that writing this Fourier series in complex form has its sometimes it is simple to compute the Fourier coefficients, for example, and this form has also direct applications in the control theory, also in other area of electrical engineering. So, we have the another example where we want to determine the complex Fourier series representation for this f x is equal to x, and it is defined in minus L to L, and again it is 2L periodic. So, the same thing, now we have the C n, this is more the general formula, and then we have the Fourier series written in this complex form. So, the Fourier series we have this, then we can compute a C n by 1 over 2 L minus L to L f x and then e power I n pi x over L. So, 1 over 2 L, that is already there, f x is replaced with x and then e power I n pi x over L, and then we can integrate by parts again. So, we have 1 over 2 L and then this x as it is, the integration of the exponential function e power I n pi x, and then this factor will be just 1 over that factor. So, it is reverse here, minus L over I n pi. Similarly, the differentiation of x will be 1, and then again this integration will come with this factor L over I n pi with a minus sign, and therefore, it has become plus here, and then we have e power minus I n pi x over L. So, we need to again differentiate here once more. So, let us proceed. So, this is the first term, then we have the second term. Out of the first term, we have to substitute first L there. So, we have L and then there is another L here. So, L will be L square with the minus sign, we have I n pi and then exponential minus I n pi, because this L will get cancelled with this L there when we are substituting the positive value of L. Then we have a minus L, again the same thing, the x will be minus L. So, and then there is a minus already. So, this minus sign will be there, and then we have again here I n pi and e power with the plus I n pi. Here again we have to integrate. So, e power minus I n pi x over L, and then there will be factor L over I n pi, which and as a result this has become now the square, and again we have to take care the limits from minus L to plus L. And this term is 0, that is the fact here, because when we put this L there, we have e power minus I n pi, and then with minus sign we have e power minus I n pi with plus sign now, because this minus L will make it plus. So, we have these two terms, and the first one is minus 1 power n and the second one is minus 1 power n, the same thing, but with the minus sign. So, this gets cancelled, and therefore, we have this value 0, and we can simplify now the first one. So, 1 over 2 L. So, this L will get cancelled with this L, the I we can multiply and divide. So, minus I square. So, both term will become positive, and we have I there, we have this 1 L there, and then e power I n pi or e power plus I n pi, both are minus 1 power n. So, we have in the very compact form this coefficient here C n as minus 1 power n and I L divided by n pi, and n varies as plus minus 1 plus minus 2 etc. So, here the C 0 we can separately compute, because this expression is not valid for n equal to 0. So, C 0 is 1 over 2 L minus L to L and f x dx. So, this is an odd function minus L to L. So, this will be 0. So, we have C 0 as 0, and finally, we can write then the Fourier series. So, the coefficient here C n I L over this pi, and then minus 1 over n, the remaining part of the C n, and we have e power I n pi x over L, and n varies from now minus infinity to plus infinity, except this n equal to 0, because C 0 is 0. So, that term will not be there in the series. So, that is the Fourier series expansion written in complex form, and now we will get to the Parseval's identity, which was already discussed in previous lecture. So, this Parseval identities in the complex form of Fourier series, because now in the Fourier series we have C n, earlier we had A n's and B n's. So, the naturally the Parseval identity will be also changed now in terms of C n, not the A n's and B n's. So, Parseval's identity in this case takes the following form. We have the similar term f x whole square dx minus pi to pi, but there is a simplified form here minus infinity to infinity C n square, that too with the absolute value. So, its solution, how to get this form, we can easily see now, because the form of the Parseval's identity from the previous lecture, we know that it was a square by 2 and there was a summation over this a n square and then the b n square, and there was a term 1 over pi from minus pi to pi f x square. So, this was the Parseval's identity which we have discussed for the normal form of the Fourier series. And now we know the relations, that how the C n, the new C n, the new Fourier coefficient is related to the old ones, and with the help of that we can convert this Parseval's identity to this form. So, recall that C 0 was A naught by 2 and the C n was half of A n minus I b n, and then C n C minus n was half A n plus I b n. That was the relation when we have used these new notations C n and C minus n. So, if we take the modulus of this C n, because it is a complex number, so the modulus will be A n square plus this B n square and 1 by 4. So, this is 1 by 4 A n square plus B n square, and the same thing will happen here. It will have the same modulus, because the only difference is that now we have the plus there, but in modulus that does not matter. So, again for C n modulus square will be 1 by 4 and A n square, and then we have this B n square. Well, so this C n square is half A n square plus B n square, and C minus n square is also the same, and we have this traditional form of Parseval's identity in hand. So, now we can convert into the forms of C n's. First, the first term A naught by 2, as it is A naught square by 4. So, we had divided here by 1 by 2 both the sides, or multiplied by 1 by 2 to the whole series. So, here the 2 will come, then here 1 by 2, and then here also 2 pi. So, this is matching exactly 1 over 2 pi minus pi to f x whole square. The first term is A naught square by 4, and now this half of this A n square plus B n square is written as 1 by 2, and so 1 by 4 plus this 1 by 4. So, this is 1 by 2, and then we have the series. So, 1 by 2 is written as 1 by 4 plus 1 by 4, and then the rest, this summation A n square plus B n square. So, what we have, the half of this A n square B n square, and from 1 to infinity, and then again we have here 1/4 and 1 to infinity A n square plus B n square. So, this is exactly C naught square, because the C naught was A naught by 2. So, here we have C naught square, and this we know already that this is A n square plus B n square, with 1 by 4 we have C n square, and then for the second one, because we have already split it into 2 to incorporate plus and minus. So, here we have this C minus n. So, we have considered this C minus n square with n 1 to infinity, and then we have the right hand side as it is 1 over 2 pi minus pi to pi f x whole square and dx. So, now we can combine all the terms. Left hand side we have c naught square, we have the positive powers of that is c 1 square, c 2 square, etc. We have also all negative powers c minus 1 square, c minus 2 square, etc. So, all these can be coupled now, and we have the whole summation which is running from minus infinity to plus infinity over this modulus c n square, and the right hand side is 1 over 2 pi and this integral minus pi to pi f x whole square dx. So, this is the Parseval's identity for the complex form of Fourier series. So, we can apply this in one of the examples in the next slide. So, the example here, given the Fourier series e power x as sine hyperbolic pi over pi, and then we have the summation here minus infinity to plus infinity minus 1 power n and 1 plus I n over 1 plus n square e power I n x. So, that is given Fourier series of e power x, and we want to deduce this value here of the summation 1 over n square plus 1, where n is from minus infinity to plus infinity. So, from the given series what we have, we can compare it now. So, the C n's are directly given there. So, these are the C n's minus 1 power n, and then we have a sine hyperbolic pi, that is e power pi, e power minus pi divided by this 2, and then there was a pi there. So, we have 2 pi, we have 1 plus I n and we have 1 plus n square, and the n varies from 0 to plus minus 1 plus minus 2, etc. So, its modulus now, because we need in the Parseval's identity. So, we can get it, and then so this is the square. So, we have positive there e power pi minus e power minus pi whole square, there will be 4 pi square term there, and then 1 plus n square whole square, and for this we have the modulus 1 plus this n square. So, the modulus of this, because all other are just a real number, they will be squared, but this 1 plus I n modulus will be 1 plus n square. And then so, here we have e power pi minus e power minus pi square 4 pi square, and then this will cancel out. So, we have only 1 plus n square. So, we have the modulus C n square ready, which is given already here, and then this is the Parseval's identity for the complex form of Fourier series, and our function is e power x. So, we will compute this other side of the Fourier series 1 over 2 pi and the f x whole square term 1 over 2 pi, we have e power x and then the square. So, e power 2 x dx. So, which is written here e power 2 pi minus e power minus 2 pi divided by this 4 pi, because e power 2 x and divided by 2 will be the integral, and then we have substituted plus pi and then minus pi there. Well, so we have e power 2 pi minus e power minus 2 pi divided by 4 pi, that the other side of this for Parseval's identity. So, this integral side we have this value, and then we have the C n square already with us. So, we have e power pi minus e power square 4 pi square, and then the summation is exactly over this 1 over 1 plus n square, that is the desired value we want to compute this one. So, that can be now given as, so this e power pi. So, this one here the left hand side we can write down as e power pi minus e power minus pi, and the product with e power pi plus e power minus pi, say a square minus b square there. So, e power pi minus e power minus pi, the one term will get cancelled. So, in the division we have e power pi minus e power minus pi, in the numerator e power pi plus this e power minus pi, and then there is a pi because of this cancellation. So, we have exactly this is the sum of this given series 1 over 1 plus n square and from minus infinity to plus infinity, which can be further written in terms of pi and the cot hyperbolic pi, which is exactly this one here, e power pi plus e power minus pi over e power pi minus e power minus pi. So, here these are the references we have used for preparing this lecture. And now, just to conclude, so we have discussed in this lecture the complex form of the Fourier series. This is the general form with this Fourier coefficients and the exponential term e power I n pi x over L, where the Fourier coefficients are computed with the help of this integral 1 over 2 L minus L to L f x and e power minus I n pi x over L dx, where n can vary now the 0 plus minus 1 plus minus 2 etc. We have also discussed the Parseval's identity and indeed used for computing the sum of a series. So, the Parseval identity was, we have just the sum of these squares of the absolute value or the modulus of C n, the sum was over minus infinity to plus infinity, and the right hand side we have 1 over 2 pi and the integral minus pi to pi f x whole square dx. So, that is all for this lecture, and I thank you for your attention.